Okay, so a review from last lecture. Welcome to lecture 12, by the way. So, we talked about supercells a little bit. We talked about how vorticity is the rotation of a fluid at a point. So, we created rotation in 3 steps. The first step was the vertical wind shear that created horizontal vorticity. So, we kind of had faster winds up top higher up in the atmosphere and slower winds at the surface, and it kind of created these horizontal tubes. It can also be the other way around, but then you have an updraft that begins to tilt the horizontal vorticity into the vertical. So the updraft takes these tubes and tilts them on their side, and then the updraft then tilts the rotating air nearly vertically, and it stretches it, which makes it rotate faster. So the second step is just the beginning of the tilting, and in the third step, it becomes almost perfectly upright, and it stretches it even more to make it faster. This rotation is called a mesocyclone. So you have cyclonic or counterclockwise rotation within an updraft. And then we talked a little bit about the supercell structure with the forward flank downdraft, the rear flank downdraft, and the updraft. So, another lecture on supercells. I think that it does deserve another day. So, we did talk about these 4 primary ingredients for supercell formation. But there's one more. So the 4 we talked about was the SLIM acronym. So shear, lift, instability, and moisture. Lift, instability, and moisture are all needed for all thunderstorms, but shear is specifically needed for severe thunderstorms. The 5th ingredient that we need primarily for supercells and not other types of storm is a low-level stable layer. So let's talk about these. So shear is moderate to strong vertical wind shear. So it's needed to tilt these updrafts away from the vertical so the storm can persist and become more severe. So it's essential for mesocyclones to form. So the shear is what creates the rotation that's tilted into the vertical and stretched by the updraft. I think they meant to say necessary to tilt up. Oh, yeah, no, it does need to be. The reason why it needs to be tilted away from the vertical, like, it can't be, like, perfectly vertical in your updraft the whole way, because if it was, then it would be, like, contaminated by the downdraft. So if you can get, like, a tilt in your updraft rather than it straight up and down, your storm can persist. So you need, like, kind of this wind shear to tilt this from horizontal into the vertical. You need the wind shear to create this spin that is then tilted into the vertical. Yeah. Yes. Okay. Lift. So this is, you need a lifting mechanism to enhance the rising motion. Yeah, lifting mechanisms cause strong rising motion to help vigorous updrafts form. However, life lessons learned the hard way. Supercells are more likely to form with a weaker lifting mechanism, and we'll talk more about this later. Like a mild to moderate lift. You don't want too much lift, or yeah, we'll talk about it. Anyway, this is a good source of overall lift to create lots of different supercells. So you had that warm sector right here, and the edge of it is the warm front. A low pressure system for these to be pulled in, these 2 fronts. So you have the dry line, and you have the cold front, and where these meet, if you have the low pressure, the dry line, and the cold front, that's called the triple point. So this is a really good place to form lift. But this kind of lift is like a broad lift, like it doesn't create that individual lift, but it can generate the environment for supercells to develop. Then the third ingredient you need is instability. So you need an unstable free atmosphere for the rising motion to be enhanced. So this helps the warm, moist air parcels to rise as quickly as possible. So if you have a cooler environment and a warm air parcel, it's going to rise quickly. 4, you need moisture. So you need this moist tropical air mass to advect inwards and add this less dense air to fuel the storm. So this air rises easily, and it also reaches saturation quickly because it's so moist. So, rules of thumb for determining conditions good for supercells. I haven't verified this myself, but it is in the slide. So temperature, the dew point depression. So the temperature minus the dew point needs to be less than or equal to 15 degrees Fahrenheit. I'm assuming this is at the surface. The temperature needs to be greater than 60 degrees Fahrenheit, and the dew point temperature needs to be greater or equal to 50 degrees Fahrenheit. Now, there's no absolutes, you can get it outside of these conditions, of course, but this is just the rule of thumb set by this PowerPoint. So, the fifth thing you need that is different from whatever else we've talked about is a low-level stable layer. And I've kind of touched on this a little bit earlier, but now we're really going to talk about it. So, when you can see right here, so this red line right here, this is the environment, and the blue line is the parcel temperature. So you can see right here, kind of a little bit closer to the surface. It's not all the way up in the atmosphere. This is kind of closer to the surface. You get this little nose, and where the environment is warmer than the parcel, and so it kind of prevents the parcel from rising for a while. So yeah, it does prevent rising motion at first, but you need this stable layer earlier on in the day. So it prevents these storms from firing too early, and it allows for more time for the surface to warm from the sun. And then what happens is it's called a cap. So it kind of keeps the cap on the storm so they don't form too early. You can wait until the right conditions. And really that energy to produce the storm starts building up. That's why they call it a loaded gun sounding when it looks like this. So when you have a small environment stable layer, it kind of keeps things at bay until the conditions are prime. And then you can erode away at this cap and it just shoots up. The air is extremely powerful and it moves up relatively quickly. Okay, so as the surface warms throughout the day, this cap is eroded. So you can see this parcel temperature moves over. So it's now warmer than the environment at all places. So parcels at the surface are so warm that the cap can no longer stop them from rising at the diabatic lapse rate. And now the parcels will rise rapidly, very suddenly. So yeah, it's a loaded gun. It creates that extra oomph. So if you don't break the cap, though, you're not going to get any storms. So the cap can sometimes come back to bite you, but it's good if you can get it to erode away. Quick reminder, what do different types of storms need to form? So an ordinary storm, you only need lift, instability, and moisture. For a severe storm, you need ordinary ingredients, so these three, plus shear. And this includes isolated storms and mesoscale convective systems. And then for the supercell, you need all of these ingredients, and you need a low-level stable layer. Well, do you need it? You want it. You definitely want it. It creates a much better environment for supercells to form. Can you get it without the cap? Probably, but it's not going to be as powerful. Anyway, rising motion can't be too strong. Just if you have a question about this, by the way, like the ingredients for supercell formation, if you get this question, wink on a future quiz, put all 5. Anyway. Sorry, my friend keeps saying and I think it's funny, so I keep saying I probably should not break that habit because it just started. Anyway, the rising motion can't be too strong. So, strong rising motion, it helps the storms to persist and vorticity to get tilted and stretched in the vertical, but very strong rising motion, lots of storms develop and likely merge into one another, so it makes an MCS and not a supercell. Yeah, also, if you get, like, very strong rising motion, the problem with that is it kind of, like, makes it harder for the storm to rotate. Like, I don't know. It can cause, like, the precipitation to, like, fling out instead of developing. Like, if you have hail, it needs to, like, have, like, that middle of the road lift so it can stay in the cloud, because if not, it's just going to get flung out. So it's kind of just important to have, like, it's like a Goldilocks thing. Like, you don't want there to be too much lift, or it's just not going to be prime for supercell formation. Like, it's kind of a delicate thing where you just need middle of the road lift. So, when rising motion is not so strong that many storms are initiated and an MCS is created, you get isolated supercells. So why is isolated so important? Also, another thing that was mentioned is the shear. You don't want the bulk shear to be ramming these storms into each other. You want it to be individual. Anyway, why is isolated so important? If supercells are too close to one another, they compete for that moist tropical air, so that's their fuel, and so there's less fuel. The outflow from one storm may get too close to another, and that can, like, cut off its updraft, because if you have a cold pool moving into the updraft of another storm, it's just going to kill it. It may disrupt the surface wind patterns and disturb the rotation and the updraft tilting. And if they were far apart, they would have a lot better chance of growing into a supercell rather than being close together. So, the lifting mechanisms are not the best for isolated supercells. So, like, cold fronts and deep troughs. You can get supercells along a cold front. It depends on the wind direction, mostly. You can get supercells along a cold front. You can get supercells along a deep trough. You just need to make sure you have enough rotation, like your shear, like your helicity, like your spin needs to be able to match up with the lift. Like, you need those two ingredients to be balanced. Yeah, but you don't really want too much lift. It can cause problems. So if you have, like, a weaker lifting mechanism, it's better for isolated supercells. So, like, dry lines are really good for forming supercells. They're very hard to predict. Warm fronts, that's questionable. Low pressure centers, short waves, short waves are very good for forming supercells. Like, if you can get a little short wave. But I would say that short waves form, like, pretty strong lift. Or, yeah, honestly, like, in my opinion, these examples, you can get weak lift and you can get strong lift, and except for, I don't understand the warm fronts. I've never seen, you don't see very many supercells form in warm fronts. Maybe sometimes out ahead of the main storm, you can get some supercells, like, ahead of the cold front boundary. Anyway, the lift is dependent upon, like, the strength of the gradient, and so you can really get supercells in any of these, in my opinion. Yeah, you can get really powerful supercells along dry lines, but they're very difficult to predict as well. But you can get supercells along cold fronts. It just depends on the wind direction. So, yeah, any of these can create isolated supercells. But if you would rather believe the slide, I get that. I get that. And it may be true that these are, like, less ideal for forming supercells, but depending on where you are, like, you can get it. It can happen. You can get supercells with these. Okay, ingredients for the supercell formation. So we were talking again about that low-level stable layer, aka the cap, earlier in the day. So when there's relatively weak lifting mechanism plus a low-level stable layer, only a few strong updrafts will break through the cap. This is good for isolated supercells because not everything will be strong enough to push through the cap, so it will give it more of that energy just for these isolated storms. And like it's not, they're not competing for energy. And you don't want them to contaminate each other either. Like, I kind of get what it's saying, but I've seen it happen. Like, this is why, the reason why I bring this up is I've seen supercells happen in cold fronts and deep troughs. So, not the best is the key word. Better is the key word. You can still get it in any of these. Anyway. Isolated supercells do not compete with each other for warm, moist, maritime tropical air. Their outflows don't interact with the other cells. This is where I'm from. This is Mississippi, Alabama. I went to school in Oktibbeha County, at Mississippi State. Yeah, we got tornadoes all the time. And yeah, they were in cold fronts. So that's what kind of why I'm biased, because you get a lot of cold front supercells to form in Mississippi. Anyway. Storms can get much stronger when they are isolated. This is true, because they can spin easier and they have more energy to feed off of. They can also persist much longer, so the longer lifetime equals more likely to produce strong and long-lived tornadoes. This is why we care... And the reason why they can persist longer is because they're self-sustaining in the way that they form. So with that updraft and downdraft being separated, and the downdraft feeding in... The rear flanking downdraft feeding the storm more, it kind of, like, creates, like, a system where it can maintain itself. Whereas if you have, like, a linear storm system, they contaminate updrafts and, like, the storms can just die really quickly. So, yeah, this is why they're more likely to produce strong, long-lived tornadoes, because they can be on the ground for a really long time. And that's why we care about how the isolated supercells form. So, isolated supercell formation, shear, weak to medium, I would say moderate, like mild to moderate lift. Not strong lift, but you know, you can have medium lift and be fine. Instability, moisture, and low-level stable layer early in the day. Here's an example of an isolated supercell. Okay, the radar image looks a little dim. This is in Oklahoma City. Okay, this was in 1999. So this was an F5. So this is before the enhanced Fujita, but it's still, you know, very powerful. Like, pretty much if you're above ground, like, I don't know. This kind of thing will, like, pull grass out of the ground and, like, pick up a train and stuff like that, and, like, just knock over buildings. So this initiated along a dry line in western Oklahoma. Oklahoma is really good for dry lines because they have that good combination of moist and dry air that butt up right against each other. Like, the farther out east, like, the less dry the air from the dry line is, but in Oklahoma you really get that good sweet spot for the dry lines to form tornadoes. So this is a dry line storm. and that's what's generating the lift on the storm. So, yeah, the supercells initiated along the dry line. Behind it, you have the cold front. So you had a squall line on this cold front, and out in front of it, you had these supercells. So I guess this is a good example of how this lift was too strong, and also the wind direction changed and created this line. The wind direction, the bulk shear is really what's important for telling storm type. Anyway, you get these like individual supercells here. You see those? Like these are powerful, and these are get rotating really easily. June 22nd, 2015 in northern Illinois, you had an EF3 in Coal City and Braidwood, Illinois. The atmosphere was, this is what the National Weather Service Chicago said. Okay, well, anyway, you can see, first, before we get into that, we'll talk about this tornado. So it was EF1 damage, and then it got to EF2, back to EF1, and then it got back to EF3 damage. Well, it got up to EF3 damage, and then it went back down to EF1. So, up to 160 miles per hour. And it lasted from 9:45 p.m. to 10:12 p.m. So it's not that long of a tornado, but it's a good 30 minutes. Like, that's a long time for a tornado to be on the ground, but you can get tornadoes on the ground for hours. The atmosphere was primed for severe weather, with very warm and humid conditions, low pressure moving north in the region, and a strong jet stream aloft. An outflow boundary from earlier storms during the late morning and early afternoon may have been key to where the long-lived tornado-producing storm tracked. Okay. I would have to think about that one. There's a link, so if you want this full article, feel free. Okay, here's a caveat. So, isolated supercells are typically the strongest and produce the largest hail and most destructive tornadoes, but other types of storms produce destructive weather as well. MCSs, yeah, we talked about those. Closely grouped supercells, yeah, and supercells embedded into MCSs. When strong supercells do form within the MCS, they usually form at the southernmost end. Yeah, because it's easier to get, like, rotation along this area. Yeah, least altered inflow. So the inflow of the storm, like, they are it's super contaminated by all the other storms. It's less contaminated on the end, and you also kind of, like, if you want to get rotation, like, it's best on the end because you can have more of that motion around the storm, whereas, like, up here, it's kind of, like, harder to get it in the line. But, oh, wow. So, the 2013 El Reno tornado, which was pretty significant, this was at the southern end of an MCS with embedded supercells. So, yeah, you can get... I think that chasing in this kind of situation, like in an MCS, I don't think that chasing MCSs is a great idea because they can move really fast, and if a tornado forms, you can get tornadoes to form like in these notches and stuff, like they're hard to see, they're hard to track, and they move really quickly, so I probably wouldn't chase out in a situation like this, but yeah, it formed in the end, where because you can get that like hook shape down there. Okay, that's the end of this. Do we have any more slides? Yes. Okay. So we just talked again about SLIM and a low-level stable layer for supercells, and that keeps the storms from firing too early in the day. Weak lift is best for isolated supercells. So it only allows a few storms to form, and it keeps the cells isolated and prevents them from merging into a long line. So, two types of vertical wind shear. Now that I think about it, I kind of get it. I get it, because if you have like really strong lift over a large area, you're gonna get more storms to form. So I think that's why it was saying that the lift can't be too strong, like over the whole line. And I agree with that. So, but it's very dependent on how strong gradients are and stuff. And yes, you can get severe weather in all of those situations. Anyway, there's two types of vertical wind shear. So you have directional shear, which is the change in wind direction with height, and you have speed shear, which is the change in wind speed with height. The type of shear you have greatly changes the type and strength of supercells. So when you have more speed shear than directional shear, you can get these splitting supercells. So there's a thing called a hodograph that maps the winds as you go up, and the hodographs look more like a straight line. And so the winds just get faster with height, but they don't really rotate that much. And it causes them to split into two different supercells, like two different tornadoes. Like you get a right mover and a left mover, and the left mover is weak and it rotates anticyclonically. So you can get a tornado out of these left movers, and a tornado that rotates in an anticyclonic fashion. Like typically a tornado will be stronger and it will rotate cyclonically, but if you use these splitting supercells, you can actually get tornadoes that rotate clockwise in the northern hemisphere. Usually not as strong. Then if you get the strong speed shear, it's associated with the cold fronts. So yeah, this is the cold fronts, like we just discussed, was the strong rising motion, and lots of storms firing along it. But if you get a lot of storms to form and the storm to split into two, you get a lot of storms. So there's a high chance that it merges into an MCS. So yeah, this is like the situation where you have supercells and then eventually they merge into the MCS. So that's like a cold front scenario. When you have more directional shear than speed shear, the storms aren't likely to split. You usually get fewer and stronger supercells. So typically that's what you look for. You look for the winds to rotate with height rather than increase with speed with height. So in the northern hemisphere, the winds in the free atmosphere are typically westerly, but you want southerly and southeasterly winds near the surface for the strongest directional shear. And this is good because it gets your rotation started, but it also brings in, like if you have southerly air, it brings in the Gulf moisture at the surface, and then it brings in dry air in the mid-levels, and so that air is able to rise as well. So you want directional shear, not speed shear, for strong supercells. And there's a case study. Okay, let's look at it. Okay, May 19, 2013. All I know, 2013 was not a good year for Oklahoma for supercell. Like, not good, like, good for, like, meteorology, but not good for the general public because, yeah. Anyway, okay, you can see the surface winds here. Moderate flow, like 15 knots, and it's coming from the south-southeast, so it's coming from the Gulf. It's pulling in this Gulf air. And let's look at the dew point. Yeah, you got dew points in the upper 60s, so that's pretty good. Up here, you have the dew points in the 70s. And you can kind of see where that front is, where the wind speed change, or the wind, I keep calling it that, the wind changes direction. It's like around here. And you can also see, I think it's a dry line because you can see the dew points go from like the upper 60s down into like the 20s. So yeah, the air is like 99 degrees and the dew point is 29. Like that's extremely dry. So this is at 925 millibars. You also, this is not at the surface, but it's a little bit farther up. You've got faster winds, so actually this is also at 15 knots right here. It's a little bit faster down here, but yeah, it's about the same direction. It's not that far up off the ground, 925, so you've got more moisture being channeled into this level as well, which is good. Then at 850, a little bit higher up, you're kind of getting more of this Mexican plateau air. So look at this wind barb. It's coming from the south. It's not coming from the south-southeast anymore, so it's not as much Gulf air. It's more like Mexico, Texas air. Then at 700, you're getting more of that dry air. This is more like the mid-levels. It's low to mid-levels. So the barb is rotating. Then at 500 millibars, which is halfway up the atmosphere, you're really getting that dry air to come in at this level. And the wind speed has changed direction significantly. Then at 300 millibars, the flow is almost westerly. It's west-southwesterly. So the wind speed is only at 30 knots, so it's not really even that fast. It's mostly just directional shear, so this is good for individual isolated supercell formation. And then 200 millibars, that's way up there, practically space, in my opinion. It's not space, but anyway, you again get this west-south-westerly flow. It's just a little bit faster. So this is good if you have upper level flow that's fast. It's good for creating a little bit extra lift. So a dry line formed and provided weak lift for the storms to form. So, yeah, here's the dry line, and there's the cold front behind it. So, this is a mesoscale discussion by the Storm Prediction Center, where they draw a, cute little bubble where they think storms are going to form. So, this is the outflow boundary of the storms. I guess a different system, so it might be from this cold front or something, but this is the, I guess this might be the outflow boundary from these storms too. Yeah, because it was being pushed up this way. Anyway, this is your dry line right here. And so this is where the storms are going to fire as this dry line progresses east. Yeah, so isolated supercells formed and so at 1 p.m. and persisted until 10 p.m. So that's like 9 hours. That's pretty good. Yeah, and these look pretty good. You've got these little notches and stuff that are forming. So, and yeah, here are the tornadoes. It was a pretty good forecast. They predicted this area would get tornadoes. There was 34 tornado reports that day. There were also some in Kansas. So that was that dry line. As it shifted more nocturnally, it probably also you have these hail reports here. So once it became more of a nocturnal storm, it shifted from probably from a supercell mode to a linear mode. So that's probably why you got more of these wind reports up here and over here. But anyway, I don't know what happened. I'm just guessing because that's what usually happens. Yeah, so in Shawnee, Oklahoma, which is east of Norman, you got an EF4 tornado. Wow. Yeah, look at that path. That's so long. It started out as a EF0, and then it became an EF1 right here, and then it let up a little bit over this lake. And it probably let up over the lake because there wasn't really anything to damage. Remember, the EF scale is a damage scale. And then you have EF2 damage, and then briefly EF3, and then more EF2 damage for a very reasonable amount of time. And then it briefly strengthened to an EF4, EF3, EF4, back to EF3, and then it continued as EF2 damage. So yeah, this is what I was saying. Most of the process of forming isolated supercells relies on balance. So you have to balance the updraft strength with the vertical wind shear to get an updraft that tilts but doesn't fall over. So yeah, you want vertical wind shear, but this is why I was saying the lift, it kind of depends, because if you have strong vertical wind shear, you're going to need a stronger updraft to like persist through that. So sometimes you can get isolated supercells with strong lift, just because sometimes like you need it to counteract the vertical wind shear. Otherwise, your vertical wind shear is going to blow the top off your storm. You need to balance your solar heating with low-level stable air to stop the parcels from rising too early. So creating that loaded gun sounding where the energy builds up throughout the day and then they fire off at the right timing. Then you want to balance having your rising motion so storms will fire, but not too much rising motion that you get too many storms and form an MCS. Right, so this is like the cold front example. Yes, you can get supercells at a cold front, but you also can get an MCS at a cold front depending on the wind orientation and how many storms form, and if those storms bleed into each other. Also, you want to have more directional shear compared to the speed shear. So you want the winds to change direction. You want them to start as southerly winds and then transition to westerly in the upper levels. And you care about that more than the speed changing with height. So this is the balance that makes the supercells more rare, because you kind of have to have all of these factors. And it really is like an art to predict when a supercell is going to happen. But with practice, it becomes a lot easier, and you'll have a lot of practice in your classes at OU predicting supercells and learning more about them. So yeah, it's a little challenging at first, but it becomes very natural and innate. So yeah, that's it for this lecture for today. So after this, 2 more lectures, and then we will be done with lecturing, and you'll just have your quiz and your final exam.